Okay, in this video, we're going to get started with Chapter 11, which is on infinite sequences and series. And so a few videos before this in the playlist was an introduction to this chapter, and mainly what we talked about was that in this chapter, we aren't introduced to the idea of a sequence or a series for the first time. That was done in algebra. And so after the introduction video in the playlist, there's included some videos from the algebra course talking about what is a sequence, what is a series, the notation, the rules, etc. Okay, and so if you've rewatched those videos from algebra, now with you're reminded of what exactly is a sequence and what exactly is a series, what we're studying in this chapter is infinite sequences and series. We're looking at a sequence and a series from the perspective of if that sequence or series has an infinite number of terms. Now, technically, any sequence or series typically a sequence or a series has a starting point. So you start with the first term or the 0th term, right? The integer input. You have to have an integer input for like a sequence formula or a series formula. That integer input usually starts at 1, but it can start at 0. But technically it doesn't have to start anywhere. It can go from negative infinity to infinity, technically. But the vast majority of the cases that you'll see when it comes to sequences and series in this textbook and in practice, they're going to have a starting point. They're going to start at 1 or start at 0 or start at 10 or they're going to start somewhere. And so the idea of an infinite sequence, mainly what we're thinking about is it has a start point, but then from that start point, the number of terms goes off to infinity. So you can think about it like the n. So, not all sequences or series you can actually write with a formula, like a function of n, where the n for any sequence or series has to be an integer. But you can think about it like if you can write a formula like that, and most of the sequences we're going to deal with you can think about it like we're looking at what happens when n goes to infinity. Right? N has a start point. N starts at 1 or 0 or some start point, and we're looking at what happens so this would be a sequence. What happens when n goes to infinity? Or if we put this sequence into a series, right? If we made a series out of this sequence by doing this, what happens when n goes to infinity? Same idea here with the sequence. That's what we're looking at in this chapter. That's what we're studying, okay? And now, what we're doing in this video, we're going to go through the opening section, which is we're looking at sequences. We're going to start by looking at sequences. Okay, and so mainly what we're going to look at is the idea of the number of terms in a sequence going to infinity. And so the section starts by giving a brief overview of what is a sequence, remind you of what is a sequence. And we're not going to get into this. That's what I included all of those algebra videos in the playlist for. So here they're talking about what is a sequence. Here they mention there's alternating sequences, the -1 to the n, -1 or to the n. You can have a formula for an alternating sequence. Here they talk about recursive formulas like the Fibonacci sequence. I included the video on recursive formulas in this playlist as well. Okay, so starting here is when we get into the calculus. We start the calculus of sequences. And so again, what we're doing is in this section, what we're doing is we're analyzing what happens as the number of terms in a sequence goes to infinity. Or kind of to restate that, it's more of what's the limit of a sequence in the sense of you can think about it like, okay, so in general, like the previous videos talk about, technically any sequence can, as far as if you think about having like the sequence has a first term, a second term, a third term, and that's what a sequence formula, not every sequence you can come up with a formula for the nth term. But you can think about it like if you could come up with a formula, then you're saying you input n. If you want to say what's the second term or the third term, you input n. You input n is equal to 2 to get the second term, n is equal to 10 to get the 10th term. And typically, the vast majority of the sequences that you see in science and engineering are going to have a start point. So, like, if you think about it from the perspective of a sequence formula, you'll be given a sequence formula like a function of n, and then it'll specify what the domain is. Like, n starts at 1 and goes to 500, or starts at 1 and goes, and it could be any value greater than 1. Right? It goes to infinity. Whatever, any number you want, any n you want that's greater than 1, greater than or equal to 1, or greater than or equal to 0. Doesn't have to start at 1 or start at 0. It can start at negative 10, whatever. But pretty much every sequence that you see, the most of them are going to have a start point. Okay? Now, and when we're saying we're thinking about what happens as the number of terms of the sequence goes to infinity, what we're saying is if we had a formula for the sequence, what's the infinity term? Like, as the number of terms goes to infinity, what is the value of what's the sequence approaching? Like, if I had a sequence formula and I put in the 100 trillionth, and I have the 100 trillionth term, what's that term going to be? Then the next term, then the 500 trillionth term, is it approaching something? Okay, most of the analysis we're going to do is going to be sequences where we do have a formula for the nth term of the sequence, but technically, you could still think about this idea even if you had a sequence that you couldn't come up with a formula for. There are some sequences that you can't come up with a formula for the nth term for. Okay, and also technically, since you could define a sequence, could be defined for, like, it goes off from negative infinity to positive infinity. You could think about the idea of what happens to the sequence as you go to as n goes to negative infinity, but that's really uncommon, and we're not going to be thinking about it from that perspective here. We're going to be thinking about it from the perspective of a sequence as a starting point, and you're kind of going off we have a start point, and we're going off to the right. Right? The infinite term, as the number of terms goes to infinity from the start point, is the sequence value? Do the sequence values approach anything? Okay. Now, what's interesting about this is, so the way they state it is we're thinking about the limit of a sequence. So they have an a sub n, but just remember, just keep it in mind. Even if you can't come up with a formula for the sequence, you can still think about this idea of a limit of a sequence. And it just says limit of a sequence, just limit. It doesn't. So what I mean by that is I couldn't say if I had the function x squared. The function f of x is equal to x squared. I couldn't say what is the limit of x squared. Right? Why not? Because there's not enough information in this question. What is the limit of x squared? What limit? What is x? I have to say what x is approaching, right? Well, with sequences, what we're gonna see is that they just say the only thing that's specified is what is the limit of a sub n is equal to a number, and that's it. And this is enough information right here. So how is this enough information? Well, the first reason is because most of the time, the vast majority of the time, it's implied that you have a limit that has a start point, because then otherwise you'd have to specify where you're talking about the going to negative infinity or going to positive infinity, right? But since the vast majority of the time the sequence has a start point, then the only kind of infinite limit is going off to like just in positive infinity. Okay, but still, you could. What if the limit of the sequence as n approaches? You could have n approaching 5, right? Don't you have to specify n going to infinity? You can't just say the limit of the sequence. And the answer to that is, so there is no. It makes no. If you think about it, and this is a really good exercise for you to think about your understanding of limits. And I would actually, encourage you could pause the video and think about, why does it make no sense to think about, when it comes to a sequence, to think about taking the limit of a sequence as n approaches 5 or 6 or 7. Saying this, the limit as n approaches 20 of a sub n. This makes no sense. And you can pause the video and think about why that's the case. Okay, so the reason is because, remember, any sequence, whether or not you have a sequence formula or not, if you think about plotting that sequence, the domain has to be an integer. Has to be. That's a requirement for a sequence formula, and even for a sequence without a formula, that's what makes sense. Because think about even a sequence without a formula, I can't say the 1.5th term, right? Like I have to say the fifth. That if I'm going to plot a sequence that doesn't have a sequence like an f of n formula, I still have to. I can still plot it, and it can only exist at the integers. It makes no sense otherwise, and so it's the same exact thing within. If you can get an f of n, an actual formula, it's the same idea. The domain of the n's has to be just integers. Okay, and so a plot of any sequence is going to be a series of dots, right? Now, okay, so with that in mind, think about if we wanted to take the limit as n approaches this value of this sequence. Well, it's not going to exist, right? That will never exist. If n is approaching any integer value, the limit will never exist. Why is that? Because remember how a limit works. You're never thinking about what's happening at the actual limit value. It's about like, okay, if I input, the way we would think about this is, okay, if I input into my sequence formula, n is, let's say this was 5. So we were saying, what is the limit as n approaches 5 of this sequence? The way we would think about it is, okay, if I input 4.999 a million nines into the sequence formula, what am I get? What's the output? Well, it's always there is no output, right? Remember how limits work. You don't care about what's happening at the limit value. Well, if that's the case, then there's no such thing as a limit of a sequence other than infinity. Because, okay, well, then maybe we do the limit as n approaches 4.5. Well, then that doesn't make sense either. Okay, so that's why a lot of times you just say, what's the limit of the sequence? Someone might ask you, or you might see a question, what's the limit of this sequence? Because the vast majority of the sequences have a starting point. They're just asking you as n goes to infinity, what is the sequence approaching? Is it approaching a finite value? Does it have a limit? Or if it just goes off to infinity or negative infinity, then you can specify that, infinity or negative infinity, which means that technically means it doesn't exist, but you put infinity or negative infinity. Or if it does, let's say it's oscillating or something, then you say the limit doesn't exist. Okay? And so so a sequence has the limit L, and we write, so the limit as n approaches infinity of a sub n is equal to L, or as a sub n, or as n goes to infinity, a sub n approaches L. All right, if it's a finite value, then the limit exists. And we say the sequence converges, or it is convergent. If the limit of the sequence doesn't exist, so if it's infinity or negative infinity, or you can't even say anything, like if it's just like oscillating or whatever, then we say that the sequence is divergent. Okay, so that's the terminology when you talk about limits of sequences. The sequence can be convergent or divergent. If the limit exists, it's convergent, which means that the limit is equal to a finite number, or if the limit goes off to infinity or negative infinity or just doesn't exist, then it's divergent. Okay? Now, when you think about the idea of graphing a sequence, and so that's what we're focusing on in this section. We want to be able to be given any sequence and answer the question, what's the limit of this sequence? And is it convergent or divergent? If it's convergent, then what's the limit? If it's divergent, then can you give me any more information? Like, is it divergent in the sense that it goes to infinity or negative infinity, or it's oscillating or whatever? Okay. Now, to be able to answer this question, to answer the question of the limit of a sequence, we can think about that. So we can graph a sequence, right? And this is helpful when it comes to limits. Graphs are helpful. And even though it's a series of dots, you can still look at this graphically And think about, okay, as this sequence goes to infinity, as n goes to infinity, it looks like it's approaching the value L. That would be the limit of this sequence. Meaning if you took the 100 trillionth term, it would be close to L. If you took the 500 trillionth term, it would be a little more closer to L. That's the idea. And the same thing here. It's like a regular function, just with the portions between the integer values erased. That's it. Okay, and so here they give a more precise definition of the limit of a sequence from that limit definition perspective, right? Remember the precise definition of the limit? Well, it's like the same exact idea, except from the perspective of a sequence. So a sequence has the limit L, and we write the limit as n approaches infinity of a sub n is equal to L, or a sub n approaches L as n approaches infinity. If for every epsilon greater than 0, there is a corresponding integer n such that so it's the integer n. If n is greater than that integer capital N, then the absolute value of a sub n minus L is less than epsilon. So yeah, it's the exact same idea as the limit, the precise definition of the limit, except now it's just that the input is this. We're talking with integers as the input. That's the only difference. And that's what it says here. If you compare definition 2 with the definition, the limit, precise definition of the limit definition, you will see that the only difference between the two limit definitions is that n is required to be an integer. Okay? And so with that, since that's the case, since they're so similar, the only difference being the input, instead of x is n, meaning an integer, then they give this theorem here. So we're going to use all of these theorems and statements to help us to find limits of sequences. Okay, so here's the theorem. It's illustrated in figure 6. It says, if the limit as x approaches infinity of f of x is equal to L. So this is a regular function with, the x is not limited to just integers. And f of n is equal to a sub n when n is an integer, then the limit as n approaches infinity of a sub n is equal to L. So this is really intuitive, and all they're saying is that if you have a function, a regular function, and you take the limit as x goes to infinity of that function, and it equals like L, or it exists and it equals a value. Okay, so you have that. That's the case first, right? Let me write this. If you have any kind of function, we learned this in chapter 2, any function to where you can take the limit as x approaches infinity of that function, and it exists, and it's equal to some number, right? So that means it's a horizontal asymptote. Okay, so this is the beginning. This is the first part of the theorem. Okay, and then if you can then also take that function, remove x, and replace it with n, meaning n is just an integer. And you might say, well, when could you not do this? Well, there could be cases where you can't do this. But then also to point out, so you might have a function that's defined, for all real numbers, negative infinity to infinity. But when it comes to the n, it depends on what your requirement is. If the domain for your n is only 1 to infinity, then as long as you can replace x with n for the domain you're interested in, and there's no issue, then then you're good, right? So, but if you can replace this function, this x with n, and let's say, n goes from 0 to infinity or 1 to infinity, and there's no issue. Like, in other words, what I mean by there's no issue, you could, plot the function like they show it here. Here's f of x, but then the dots are f of n. If you could do that with no issue, for the entire domain from n is equal to 1 to infinity, then you can just go ahead and say that the limit as n goes to infinity of f of n is equal to L. This is if this is the case, if this is true, and you're able to do this with no issue, make f of n, then this limit is true, and then the limit of the sequence then is equal to L. And this makes sense because look, here again, here's the function. The continuous curve is the f of x. F of n is just the dots, right? Well, look, then the limit of the sequence as n goes to infinity is the exact same thing as the limit of the function as n goes to infinity. Okay, so this is one of the main theorems we're going to use to get limits of sequences. You're given a sequence formula or whatever, and you just look and see, okay, well, could I make this sequence formula? Could this be an f of x, and there wouldn't be an issue, right? I'll be given a formula for a sequence, a f of n. Could I just replace n with x, and that's no problem at all? If you can, then just take the limit as x goes to infinity to get the limit. Okay, so they give an example here of, so like we know that the limit as x goes to infinity of 1 over x to the r is equal to 0 when r is greater than 0. This is one of the limits we studied. And so since you can just replace x with n, and that's no issue, then the limit of this sequence if we have a sequence with a sub n is equal to 1 over n to the r, where r is greater than 0, then the limit of that sequence is equal to 0. What does that mean? If you took the 100 trillionth term of this sequence, it's going to be close to 0. That's the idea. As you go way down to infinitely down the sequence, going to the right, it's going to each successive term is going to be closer and closer and closer to 0. Right now, if a sub n becomes large as n becomes large, then we say that the limit is equal to infinity, right? It's similar to regular limits, right? And so here they give the definition of a sequence that goes to infinity, the precise definition. And it's the exact same idea as what we did for regular limits, except that the n is an integer, right? So for every positive number capital M, there's an integer capital N such that lowercase n is greater than n and a sub n is greater than m. This is like the precise definition of the limit that goes to infinity, the infinite limit. And so if the sequence goes to infinity or negative infinity, then the sequence is divergent, but in a special way. And so we specify that the sequence is divergent, but we can give a little more information. We say it goes to infinity or negative infinity. Okay, now here they give limit properties, these are like parallel to the limit laws that we learned in section 2.3. So if we come back to section 2.3, these were the limit laws. Okay, now it says here, these limit laws for general limits also hold for limits of sequences, and their proofs are similar. So there's no differences. The same limit laws, what they're saying is the same limit laws that we just showed for regular limits, all of those hold for limits of sequences. And the reason why that is, you can think about just looking at this. Okay, now it says here, the squeeze theorem can also be adapted for sequences. So there's like a parallel to the squeeze theorem. If a sub n, a sequence a sub n is less than or equal to b sub n, is less than or equal to c sub n, which when it's saying that that's like the terms, right? You can kind of think about it. You could think about it like if you had a sequence formula, an f of n, but it doesn't have to have a sequence formula, but that's kind of the way you can think about it. Even if it doesn't have a sequence formula, you can kind of imagine if it did. That's the idea. So a sub n is less than b sub n is less than c sub n. Then for n is greater than or equal to n naught, and the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of c sub n is equal to L. Then the limit as n approaches infinity of b sub n is equal to L. So yeah, it was c sub n is greater than or equal to b sub n is greater than or equal to a sub n. So this is like what they're showing here. The sequence is, this b sub n is always in the middle of these two, at least for like n is greater than or equal to n, some starting point. And then if the limit as n approaches infinity, in this case, we're talking about infinity, if the limit of c sub n is equal to the limit of a sub n, and they're equal to a number, then the limit of b sub n, as this is going to be as n goes to infinity, is also equal to that number. Okay, so that's the squeeze theorem applied for sequences. All right. Another useful fact about limits of sequences is given by the following theorem. So this theorem is unique to sequences. There's no parallel for this for regular functions. So we're looking at the limit as n approaches infinity of the absolute value of a sequence. And you can think about this from the perspective of like an alternating sequence, right? So if you have a sequence where the sequence formula has like a -1 to the n in it, how do you analyze the limit of a sequence like that? Well, this is one of the main formulas. You take the absolute value of that sequence, so you can remove that -1 to the n from the formula. If the limit as n approaches infinity of the absolute value of the sequence is equal to 0, then the limit as n approaches infinity, or just the limit of the sequence is equal, of the general sequence is equal to 0. So yeah, that's powerful, especially for alternating sequences. You just remove that -1 to the whatever to just make it always positive, and then you take its limit. However, though, it doesn't say that. This doesn't say L here. Notice that it doesn't say L. It only says 0. It doesn't give us any guidelines for if you take the absolute value of a sequence, and then you take the limit, and that equals a number other than 0, then it doesn't tell us, then what does that mean for the actual sequence without the absolute value on it? It doesn't tell us anything from that perspective. Only if the limit of the absolute value of the sequence is equal to 0, then we know that the limit of the sequence itself without the absolute value is equal to 0. Okay, so here they give some examples. We're going to work a bunch of examples. Okay, here's another theorem we can use. The following theorem says that if we apply a continuous function to the terms of a convergent sequence, the result is also convergent. So what they're saying here, they're saying apply a continuous function to something. What you can think about is, so if we have a sequence, and let's say there's a sequence formula, a function of n, then you could apply the sine function to it by doing this, which just means you're taking the sine of every single value of the sequence. That's what they're saying by apply a function to it. And so, but the theorem, what the theorem states is that if you've got starting with the sequence, you're not thinking about the function to start, and that sequence has a limit equal to L. The sequence converges and the limit is equal to L, and then you have a function f that's continuous at that limit value. So it doesn't have to be continuous everywhere, just continuous at that limit value. Then the limit of this, the function applied to the sequence, is equal to the function evaluated at that limit value. And so, this is powerful because the vast majority of the functions that we know of from algebra and trigonometry, they're continuous everywhere. But really, they only need to be continuous for like x is greater than or equal to 0 or 1. Most of the, x, the power functions, the sine function, cosine, the square root, right? Square roots are continuous for all x greater than 0. They're continuous everywhere. But even the ones that aren't continuous everywhere, they're continuous at most places. So like 1 over x, right? You can't divide by 0, but for any x greater than 0, it's continuous. Like a tangent function is, it kind of is periodically not continuous. So maybe a tangent function wouldn't work well for this theorem, again, because you're periodically dividing by 0. But what I'm saying is that even if you have a function that's not necessarily continuous everywhere, this isn't saying that the function has to be continuous everywhere. It's just saying it has to be continuous at the limit value of the underlying sequence. Okay, so if we look at this example, the limit of sine of pi over n, well, we see we have the sine applied to we could look at this as a sequence function, pi over n. And so we can find the limit of pi over n, just the sequence pi over n, that's 0. And then we're not saying is sine continuous for the entire domain of pi over n, of the sequence pi over n. We're saying is sine continuous at the limit value of pi over n, which is 0. sine is continuous at 0, so the limit of the sequence sine of pi over n is equal to sine of 0. Sine of the limit of this sequence, of the sequence pi over n, which is 0. So that's the limit of sine of pi over n. Okay, now what they talk about next is when it comes to sequences, in particular sequence formulas, this is one of the main areas that factorials come into play. And why is that? Well, because remember, the domain of a factorial is only integers. There's no such thing as 1.5 factorial. The domain of a factorial is only integers. Okay, so it says in this example, discuss the convergence of the sequence n factorial over n to the n power. And so it says both the numerator and denominator approach infinity as n approaches infinity. But here we can't just replace n with x and maybe use L'Hopital's rule, because, the derivative of x factorial, even if you restricted x to just the integers, is not going to be it does have a derivative, but it's like an out of the ordinary function. But even so, you can't just replace n with x and analyze it that way. So when it comes to sequence formulas that involve factorials, a lot of times we're going to have to do like a manual analysis, write out the factorial kind of manually and see if we can simplify and get an idea of what the limit would be. And so what they do here is they write out a few terms. So a sub 1 is 1, a sub 2 is 1 times 2 over 2 times 2, a sub 3 is 1 times 2 times 3 over 3 times 3 times 3. And then here's a sub n written out. And so it seems like, just looking at the formula, and they actually do the graph here, that this limit, as n gets large, the a sub n gets closer to 0. And the reason is because you're always multiplying by the same value in the denominator. And then in the numerator, it's like 1 times 2 all the way up to that value. So, but like you can never have the final value in the numerator multiplication is never going to be bigger than the term in the denominator, right? It'll always be like 1 times 2 times 3 times 4 times 5, and then 5 times 5 times 5 multiplied the same number of times. So just looking at that, you can see there's no way you could have a sub n be greater than 1 ever. And so, but you would think, just intuitively, as n gets large, this is going to just get really small, approaching 0. But how do you prove that? And so what they do is they factor out a 1 over n from the a sub n formula, okay? And then they make the statement that, so this can never be greater than 1. It can only be less, it's going to be between 0 and 1. And that's the case for this, too. But for the sake of the proof, they're saying they factor out a 1 over n, and they're saying, even so, even though you factor out the 1 over n, this is still the case that this is going to be between 0 and 1 for all n. And so what they're going to say is that, in that case, we know, since this is going to be between 0 and 1, we know that a sub n is going to be between 0 and 1 over n, right? Since this is between 0 and 1, we know that a sub n is going to have to be for all n between 0 and 1 over n. And if we come up here, that's what they state here. And so with that, we can use the squeeze theorem. You take the limit of this, both go to 0. And since the actual sequence itself is sandwiched in between these two for all n, then the limit of a sub n is also 0. Now, the squeeze theorem is difficult to use to figure out how to use it. It's not like every time you deal with a factorial sequence, you'll have to use something like the squeeze theorem to solve it. In general, the idea is going to be you're going to have to kind of just write out the factorial. Like if you had, for example, if you had n plus 1 factorial, then you write this as n plus 1 times n factorial, or n plus 1 times n minus 1 factorial. However you need, that would help you simplify the problem. It depends on what you've got like in the denominator, and you'll kind of solve it that way. Okay, let's take a look at this example. It says, for what values of r is the sequence r to the n convergent. Okay, so you can have a sequence formula that involves non-integers. That's fine, but just the input's going to have to be the input's going to have to be an integer, and that's what the n is. Okay, so it says we know from section 2.6 and the graphs of the exponential functions from section 1.4 that so the limit as x approaches a of a to the x is equal to infinity for a is greater than 1, and it's equal to 0 for a is between 1 and 0. Right? We talked about this in section just exponential functions and also limits. If you've got a to the x, if a is greater than 1, this limit then goes to infinity. If a is between 0 and 1, this limit goes to 0. If a is equal to 1, the limit goes to 1. If a is equal to 0, the limit goes to 0. Okay, and so with that, we can just say a is equal to r. So they're saying now we're going to do the r to the n. So now we're just saying that n is an integer instead of just x is any real number. And from the theorem where we can just replace x with n and analyze it, there's no issue, right? So that the theorem where we take a function like a to the x and just replace the x with n, and then but we can just match up the limit. We can look at the limits of the function, and then if we can replace x with n and there's no issue, then we can just match up those limits. Those limits are the same. Well, there's no issue. Is there any issue here doing if we had a to the x and then we switch that to a to the n? Is there any issue there? Well, no. Think about the graph of an exponential. Is there any issue with the graph of an exponential because it's continuous everywhere? Just erasing the parts of the function that are not at integer inputs, and just you're left with dots. No. So what they're saying is with that, then we can whatever the limit is of this as n goes to infinity is going to be the limit of the sequence, this sequence, which is r to the n. Okay, and so as n goes to infinity of r to the n, it's infinity if r is greater than 1. It's 0 if r is between 0 and 1. If r is equal to 1, the limit is equal to 1. If r is equal to 0, the limit is equal to 0. Now, notice, I'm not saying that we're not taking limits of sequences approaching specific values. We're saying that for r to the n, if r is greater than 1, then the limit of the sequence is infinity as n goes to infinity. If r is between 0 and 1, the limit of the sequence then is 0. If r is equal to 1, then as n goes to infinity, the sequence is equal to 1, the limit of the sequence. If r is equal to 0, the limit is equal to 0. Okay. Now it goes further and says, okay, what if r is between 0 and negative 1? Then what would happen there? So if you had it's going to be an alternating sequence because if you had negative 1/2 to the n, well, okay, n is equal to 1, you've got negative 1/2. N is equal to 2, you've got 1/4. N is equal to 3, you've got, right? It's an alternating sequence, but we can use the absolute value sequence theorem. We can use that theorem that deals with the absolute values of sequences. So the absolute value of r to the n is just the absolute value of r to the n. Right? The absolute value of this is what? Just 1/2 to the n. So with that, if r is between negative 1 and 0, then the limit of the absolute value of r to the n is just going to be equal to 0 because you're going to be left with just positive, or you're going to be left with the sequence where r is between 0 and 1, which we know is 0. And so based on that theorem, if we come back, we can apply this theorem because the limit of the absolute value of the sequence is equal to 0. We can apply this theorem. Okay, now if r is equal to negative 1, the limit doesn't equal 1. The limit doesn't exist. It's divergent. And why is that? Because you're going between negative 1 to the n is oscillating. whereas 1 to the n isn't oscillating. And then if r is less than -1, it diverges, but it doesn't diverge like if r is greater than 1, this limit goes to infinity. If r is less than -1, the magnitude does balloon to infinity, but it's oscillating between positive and negative. So you can't say it diverges to negative infinity or positive infinity. It's just it's an oscillating divergence. Okay, so they summarize all of this here. The sequence r to the n is convergent if r is greater than -1 and less than or equal to 1, and divergent for all other values. But if it's greater than 1, you can actually specify the divergence. The divergence is infinity. If it's less than -1, you can't. It's oscillating. Okay, so a few more things to talk about in this section. A sequence is called increasing if a sub n plus 1 is greater than a sub n for all n is greater than or equal to 1. That is, so like a sub 2 is greater than a sub 1, a sub 3 is greater than a sub 2, and it's decreasing if it's the opposite of that, for n is greater than 1. And it's monotonic if it is either increasing or decreasing. Okay, so the technical definition of increasing and decreasing is for all n is greater than or equal to 1. It's the case that every successive value is greater than the one before it if it's increasing. For all n is greater than or equal to 1. So it's not saying that like this, if this is, maybe this is the case for a sequence when once n gets to 50, then every single successive value is greater than the previous value. Then according to this definition, it's technically not an increasing function, technically. I mean, I think what they're saying here, we're looking at 1 like being the start point. So an increasing sequence is every single successive value is greater than the previous value. And decreasing is every single successive value starting from the start, from the first term of the sequence is less than the one before it. That means it's an increasing or decreasing sequence. And then if a sequence is increasing or decreasing, then it's called monotonic. All right. So you could imagine like a rational function like this, 1 over n, for example, is decreasing. You start off at n is equal to 1, where most sequences start, and then every single n after that is always less than the n before it. Or every single term, not n, like every single term is going to be less than the term before it. It's all the way from the start. So it's a decreasing sequence. Okay, and again, note this definition is not saying that it's not increasing or decreasing in the beginning, but once you get to like n is equal to 50, when n is greater than or equal to 50, it's increasing or decreasing. Then it's technically not, by definition, an increasing or decreasing function. It needs to be that way from point 1. Okay, so another definition is a sequence is bounded above if there is a number capital M such that a sub n is less than or equal to m for all n is greater than or equal to 1. Okay, so again, you can kind of think about it. Well, let's look at this. Bounded below if it's the opposite, right? There's a lowercase m. And so you can think about it like where the start point is n is equal to 1. So a sequence is bounded above if every single value of the sequence, as the number of terms go to infinity or whatever, is less than or equal to a number. A finite number. Not infinity, like a capital M is a number. Every single term of the sequence is less than or equal to a number, then it's bounded above. If every single term of the sequence is greater than or equal to a number, then it's bounded below. And you could just notice that by definition, this is kind of a trivial case, but like if you had r to the n when r is equal to 1, right? Well, every single term of this sequence from n is equal to 1 to infinity is equal to 1. So this is bounded above and below. So m is equal to 1 and m is equal to 1 because it says less than or equal to m. Every single value of this sequence for infinity is less than or equal to 1 and also greater than or equal to 1. Again, that's like a trivial case, but I'm just trying to give you a sense of this definition. All right, now if a sequence is bounded above and below, then it's called a bounded sequence. Okay, so just to give an example, you can think about like a exponential. You know, it starts off, it does like this, but so it starts here though with n is equal to 1. I guess it starts here. It's bounded below by this value. Technically, the entire function going from negative infinity to infinity is bounded below by 0. But if you're starting at 1, it's bounded below by this value, and it's not bounded above. There's no capital M. You can't find a capital M. But if it's bounded above and below, then it's called a bounded sequence. Just in general, not bounded above, not bounded below, just bounded. Okay, so with these definitions, it says that we know that not every bounded sequence is convergent. So bounded, it means it's bounded above and below. That's interesting. You would think that it would be, okay, well, no, I know what a good example. Think of an example. How could you have a bounded sequence that's not convergent? So it's bounded above and below. Well, think about the sine function or the cosine function. That's bounded between -1 and 1, but it's, as n goes to infinity, if you turn that into a sequence, it's not convergent, right? It's oscillating. So we know that not every bounded sequence is convergent, or -1 to the n, right? That's oscillating, okay? And also not every monotonic sequence is convergent. So not every bounded sequence is convergent, and also not every monotonic sequence is convergent. Monotonic meaning it's either increasing or decreasing. Well, that makes sense because it's not, a monotonic sequence would e to the x, right? That's monotonic. It's increasing for all x or all n, but that's definitely not convergent. Okay, but if a sequence is both bounded and monotonic, then it must be convergent. All right, so again, but if a sequence is both bounded and monotonic, then it must be convergent. So that would be something kind of like this. You know, we've seen functions. I want to say this is like inverse tangent maybe. Right? Now you would start at like n is equal to 1, so you'd ignore all this. But okay, but it's bounded below and it's bounded above. So it's bounded and it's monotonic increasing. So that means it must be convergent. The limit as n goes to infinity must exist and be a finite number. And so the proof of this is based on the completeness axiom, and we're not going to get into all that. So that the monotonic sequence theorem, every bounded monotonic sequence is convergent. And they give the proof here. Okay, now the last example, they analyze a sequence that's defined recursively. So, you know, you want to be able to be given any sequence and analyze it and see what its limit is, right? Analyze any sequence from a calculus standpoint. And so what they're going to do here is we're going to prove that this sequence is increasing and it's bounded, and therefore it must be convergent. And then we could also figure out what it converges to as well. And so here's the sequence defined recursively. A sub 1 is equal to 2. A sub n plus 1 is equal to 1/2 times a sub n plus 6. For n is 1 to infinity. Okay, so yeah, it's defined recursively. And so they write out the first 9 terms, and what you can see is that if we come, it looks like 2, 4, 5, 5.5, 5.75. It looks like it's an increasing sequence, and it's bounded above and below, bounded below at 2 and above at 6. Okay, but to prove this, we're going to use mathematical induction. Now, this isn't a course for math majors, math PhDs, but we do learn mathematical induction in algebra, so I included that video as well before this video from the algebra playlist. And so with induction, you can prove that something is true over a set of integers, specifically positive integers, but that's typically the case, most of the time the case with the kind of sequences we're dealing with, where it's like the n starts at 0 or 1 and goes up from there. And so we're going to use induction. What do we need to prove? We need to prove that this is an increasing sequence, and that we can also use induction to prove that it's bounded. And so, okay, with induction, to prove that it's increasing, we're trying to show that a of n plus 1 is greater than a sub n for all n greater than or equal to 1, all positive integers. So what you do is, with induction, you say that you prove that it's true for the first term, or in this case it would be the second term. So like a sub 2 is like, you plug in n is equal to 1, the first term. That means that a sub 2 is greater than a sub 1. Yes, that's true. 4 is greater than 2. You're kind of, this is a little confusing because we're like the first term uses k plus 1, but so we assume this is true, that like a sub k is true, that with just the statement with at k is true. So the first, like, you replace n with k, and what are we saying? Like we come here, right? We're trying to show this a sub n plus 1 is greater than a sub n for all n. We plugged in n is equal to 1. We showed that's true. Now replace this with k, and we assume this is true. Now we want to show that like the successive term is true. And so, okay, we add 6 to both sides. Then they divide both sides by 1/2, so you don't have to flip the inequality or anything. And then, okay, 1/2 a sub k plus 6. That's a sub k. If we come here, that's a sub k plus 1. Okay, a sub k plus 1. 1/2 a sub k plus 1 plus 6. That's going to be a sub k plus 2. So we've shown that for the next term that this is true. So that's induction. We've proved that it's true for all n. So we proved that it's an increasing sequence. Next, we want to show that a sub n is bounded by showing that a sub n is less than 6 for all n, because we can see clearly that it's bounded below at 2. But how can we prove that it's bounded above at 6? So, okay, is the first term less than 6? Yes, it is. So now you suppose that you replace n with k, and you assume that a sub k is less than 6. You assume that's true. Now you want to show that a sub k plus 1 is also less than 6. So you add 6 to both sides, divide both sides by 2, and this is a sub k plus 1. That's less than 6. So it's bounded above, and we know it's bounded below. So this is bounded in general, and it's monotonic. So we know that it must be convergent. Okay, but it says here, we've proven it's convergent, but it doesn't say it. We haven't shown anything about what it converges to, what the value of the limit is. All right, but now that we know that this limit exists, we can use the given recurrence relation to write, so limit as n approaches infinity of a of n plus 1 is equal to the limit as n approaches infinity of this is a of n plus 1, right? That's if we come back here, that's where they're saying they took the limit as n approaches infinity of a sub n plus 1, and then that's equivalent to the limit as n approaches infinity of this. Okay. So we're here. We can take out the 1/2, and now with the limit laws, we can kind of take the 6 out of here. What they're doing is, it's like you can say this is equal to the limit as n approaches infinity of a sub n plus the limit as n approaches infinity of 6. But the limit as n approaches infinity of 6 is just 6. So what you've got is 1/2. This limit as n approaches infinity of a sub n is just L. Well, okay, they actually already did. So, all right. Yeah, they can apply this limit just to the a sub n, right? You could take out the 1/2, that's obvious. But then you have the limit as n approaches infinity of a sub n plus 6. You can put that limit to each of those values, but the limit as n approaches infinity of 6 is just 6. So you're left with just this limit, the limit as n approaches infinity of a sub n, which is L. But if the sequence a sub n approaches L, then the sequence a sub n plus 1 approaches L, right? It's kind of like the same. A sub n plus 1 is this, as far as n going to infinity, it's the same sequence. So you get this equation here. Solve for L, and it's equal to 6. Okay, so now let's work some example problems.